Okay, let's dive right into this. Welcome to The Explainer. Today, we're unpacking a seriously fascinating piece of modern computing architecture. We always hear about CPUs and GPUs, right? But how do they actually talk to each other? How do they team up to absolutely crush high-performance computing tasks? Well, today we are demystifying the CUDA Execution Model. We're going to explore the literal step-by-step choreography that allows standard processors to offload their heaviest mathematical burdens to the massive parallel processing power of a graphics card. If you've ever wondered how real hybrid programming works under the hood, you are in exactly the right place.
Here's our quick roadmap for today. We'll start with the traditional C program flow, look at the GPU coprocessor solution, move into setting up hybrid memory, cover execution and data transfer, and wrap it all up with a complete CUDA summary. Let's get to it.
Section 1. Traditional C program flow. We've got to establish a baseline here.
If you've ever written code in C, or really any similar language, this 7-step process, it's practically muscle memory. You know the drill. You include your libraries, declare your variables, allocate memory to those variables, and initialize them with your data. Then, the CPU does the heavy lifting. It runs the computations, stores those results, and finally, assuming you don't hit a nasty segmentation fault first, it frees the variables to release the memory. It's super reliable and it handles standard logic beautifully, but it really begs a massive question. What happens when those computations involve huge datasets or insanely complex physics simulations or deep learning models? What happens when the math just gets overwhelmingly heavy for a single processor to handle one step at a time?
Section 2. The GPU coprocessor solution. This is where we start accelerating tasks.
So let's clearly define the GPU's real role here. In this modern architecture, the GPU acts as a coprocessor or an accelerator. Basically, it's a secondary processor purpose-built to handle incredibly computationally intensive jobs that we deliberately divert away from the main CPU. Think of it like a manager and a worker. The CPU, that's your highly intelligent general-purpose manager who handles all the complex logic and keeps the whole system running smoothly. The GPU, on the other hand, is a highly specialized, hyper-focused worker designed to do one thing ridiculously fast: massively parallel computations. The manager doesn't do the heavy lifting, they just delegate it to the worker.
Check out the flow of delegation here. You've got the CPU acting as the main control center, right? And it has its own dedicated memory, the main RAM. When the CPU hits a standard task, it just processes it and spits out the results. Easy. But when it hits a severely compute-intensive task, it delegates that specific job over to the GPU. And here's the kicker. The GPU doesn't use the CPU's memory. It operates in its very own isolated workspace called VRAM, or video RAM. Once the GPU finishes crunching those numbers, it passes the results right back to the CPU, which just picks up its control operations exactly where it left off.
So, just to contrast these two distinct roles crystal clearly, the CPU handles the control logic of your program using its own system RAM. The GPU solely handles compute-intensive tasks using its own isolated VRAM. This is an absolutely crucial concept because it means these processors live in two totally different hardware and memory worlds. They literally cannot reach into each other's brains to grab data. If our manager wants the worker to process a massive spreadsheet, the manager has to physically hand a copy of that spreadsheet over to the worker's desk. They need a bridge.
Section 3. Setting up hybrid memory. Let's get these spaces prepared.
Okay, so here are the first 4 steps of the 9-step CUDA program execution model, and you'll probably spot a theme right away. We are mirroring our setup. Step 1, we declare variables for the CPU. Step 2, we allocate memory for those variables in the CPU's main memory. Now, because the GPU absolutely needs its own space to work, we basically duplicate this entire process on the accelerator side. Step 3, we declare separate variables specifically for the GPU. And step 4, we allocate memory to those variables over in the GPU's isolated memory space. We're essentially building 2 identical staging areas, one on the manager's desk and one on the worker's desk, getting everything perfectly staged for the data.
Section 4. Execution and Data Transfer. It's time to unleash that compute power.
This illustrates the exact moment that bridge is finally crossed. At this stage, our data has been initialized in the CPU's main memory, but the GPU, it still can't see it. So a physical copy of that data has to be transferred across the system bus, moving all the way from the CPU main memory directly into the GPU memory. Now look, this is a computationally heavy operation, which is exactly why CUDA programmers bend over backward to minimize these transfers. But it's absolutely essential. You literally have to get the data into the worker's hands before they can do their job.
So let's walk through how these final steps play out sequentially in our model. Step 5 is initializing the data in the CPU memory.
Step 6, as we just saw, is copying that data from the CPU memory over to the GPU memory. And then we hit Step 7. This is the pivotal moment of the entire process, guys. The CPU issues the command, officially instructing the GPU to begin parallel execution. The GPU springs into action, firing up thousands of tiny cores to crunch all that data simultaneously. Once the computation is totally finished, we hit Step 8. The results are copied back from the GPU memory to the CPU memory so the main program can actually use them. And finally, Step 9. Just like any responsible C program, we clean up our mess by freeing both the CPU and GPU memories. The whole shebang.
Section 5. The complete CUDA summary. Let's look at the complete flow.
So if you take away one crucial point today, make it this. CUDA is not about replacing the CPU with the GPU. Not at all. It is a powerful hybrid programming model. It's all about synergy. You're taking a standard program and strategically bypassing the computationally intensive tasks to the GPU. By treating the GPU as a dedicated coprocessor or accelerator, you really do get the best of both worlds. You get the complex logic and fine control of the CPU, paired perfectly with the raw, massive parallel calculating power of the GPU.
Now sure, it takes a bit of setup to manage those two completely separate memory spaces, but when you master that 9-step flow, you unlock some seriously incredible performance. So I'll leave you with this. Now that you understand exactly how the CPU and GPU collaborate under the hood, I want you to look at your own software projects. Where is the math bogging down your system? What compute-intensive bottlenecks are you going to accelerate next using the CUDA Execution Model? Thanks so much for hanging out with me for this explainer, and happy optimizing.